nomination. I'm going to put a link in the chat that you can go to that shows all of the previous seminar series as well as the nomination form, and it'll take you to a Google form. Self-nominations are encouraged, so if you're a student or a postdoc and you want to present, please do. But anyone who's more established in the field, please nominate any early career scientists that are working with you. So we'll get started today with our first speaker, is Jason Alford. Dr. Alford did his PhD in physics at Columbia University, working with Jules Halpern, and he's currently a postdoc at NYU Abu Dhabi. His research is focused on observations and modeling of various classes of isolated neutron stars, including their associated pulsar wind nebula and supernova remnants. So Jason, please unmute and share your screen.
Thank you for the introduction. Okay, can you see my screen?
Yes, looks good. Take it away.
Okay, so thank you again for the introduction and inviting me to speak about my recent work on this pulsar wind nebula shown here in this nice Chandra image. So this talk is based on work I've done in collaboration with Guobao Zhang and Yossi Gelfand, and we just recently submitted our paper to APJ. So to just quickly outline this talk, I'll give some background on gamma ray sources and pulsar wind nebulae, and then this particular G54 system. Then I'll talk about the NuSTAR and XMM observations that we analyzed. And then I'll get into the details of our spectral analysis and SED modeling, and then say a little bit about some X-ray timing of the pulsar, and then draw some conclusions and talk about future work. So now let me just give you some background on pulsar wind nebulae as high energy TeV sources. So recently, the LASSO Observatory released their first catalog of 90 TeV sources, some of which are detected actually beyond 100 TeV. So many of these sources are actually pulsar wind nebulae, and they're producing the observed gamma rays via the inverse Compton mechanism. And to produce these very high energy photons observed by LASSO, the target photons will have to be CMB photons, in which case this equation here applies, and we can see that to reach energies greater than 100 TeV, you need at least approximately 200 TeV leptons. So as you might imagine, some of the youngest and most energetic pulsars are associated with these very high energy gamma ray sources. As we can see on the plot on the right here, that shows some pulsar spin down powers and their characteristic ages, and if they're colored red or blue, that indicates if they're a X-ray or gamma ray source, respectively. So, of course, the pulsar in G54 is one of these young and very energetic pulsars with an EDOT of about 10 to the 37 ergs per second and about a 3,000 year characteristic age. So now I'll show you what the LASSO Observatory saw in the G54 region. So here's the LASSO view of the part of the galactic plane where G54 is located, viewed in 3 gamma ray energy bands from 1 to 25, above 25, and beyond 100 TeV. So we can see that the LASSO source J1929 overlaps the position of G54. If you look at 54 degrees galactic coordinates here. And it's detected in both detectors in these 3 energy ranges. And it's among the only 43 LASSO sources with clear emission beyond 100 TeV. So, of course, these leptons producing these gamma rays will also produce X-ray synchrotron, and of course synchrotron all the way down to radio. And what we did is we looked at combined XMM and NuSTAR data to confirm G54's association with this LASSO source. But before I show you the XMM and Chandra data, I'll just quickly introduce you to the G54 system. So you can think of G54 as sort of an older cousin of the Crab Nebula, with the Chandra data in blue here showing it's very similar to the Crab. It has this center-filled X-ray morphology with a ring and jet structure. And also there's no obvious hot supernova remnant ejecta surrounding the PWN. So here, there's also in this image some Spitzer data shown in green and red, and it indicates that this particular pulsar wind nebula is in a very dusty environment, and studies of the dust composition and mass indicate that the progenitor star probably had approximately 16 to 27 solar masses initially. And they also discovered that there are some OB stars embedded within the supernova ejected dust. So maybe this was the most massive and first star to explode in this cluster. So now I'll show you the NuSTAR and XMM observations. Combined, they cover energy range from approximately 0.5 keV all the way up to almost 80 keV. And we can see that G54 is clearly detected in each observation, but you'll notice that unlike in the Chandra image, the XMM and NuSTAR data don't have the angular resolution required to resolve the pulsar from the PWN. So in order to accurately measure the pulsar wind nebula spectrum, what we did is we used a previous Chandra study of the pulsar and fixed its emission, fixed its spectrum, and then attributed the excess to the pulsar wind nebula. So here's what we found when we did this spectral analysis. So we modeled the pulsar as a pure power law, and the pulsar wind nebula, we found a broken power law was required to fit the data. And what was very interesting is that we found that there's a break in the pulsar wind nebula spectrum around 5 keV, and that the magnitude of this break is consistent with synchrotron cooling. So if this actually is due to synchrotron cooling, then we can take the estimated about 3,000 year age of G54 and then calculate that that corresponds to an average magnetic field strength of around 5 microgauss. And that's all, of course, assuming that this break is due to synchrotron cooling. So now, once we have the pulsar wind nebula spectrum, what we did is we combined this new X-ray data with multi-wavelength data from radio to gamma rays, and we modeled the SED with a time-dependent one-zone model developed by Gelfand et al. In 2009. And in this model, the pulsar continuously injects a spectrum of energetic particles into the pulsar wind nebula, and then the model self-consistently tracks the particle spectra as they radiate. So the model inputs are just basic physical properties of the pulsar, the supernova remnant, and the pulsar wind nebula, such as the observed pulsar spin parameters today, the initial pulsar wind nebula particle spectrum, and the supernova remnant explosion energies to give you a sense of what the input parameters are. And I'll show them explicitly on the next slide. And so then the model outputs the SED and the size of the pulsar wind nebula. So now I'll show you the results of our modeling. So here you can see that we were able to achieve a good fit to G54's SED. The XMM and NuSTAR data were critical to derive some of the system parameters that couldn't be derived previously. And especially interesting now in light of the new LASSO gamma ray catalog. So in particular, notice that we find the maximum pulsar wind nebula particle injection energy is around 400 TeV, and this is consistent with the LASSO detection of photons with energies above 100 TeV. We're also able to derive a pulsar initial spin period of approximately 70 milliseconds, compared with its period today of approximately 130 milliseconds. And we were able to derive a true age of the system of 2.8 thousand years, similar to the characteristic age of around 2.9. So now I just want to highlight some of the astrophysical implications of these results of our modeling. Um, so the most important result, as I said, is that G54 is capable of powering the LASO source that's coincident with it. And another interesting thing is that we found that 7 microgauss pulsar wind nebula magnetic field predicted by the model is very close to the 5 microgauss field, which can be calculated just by assuming that the break in the new star spectrum was due to synchrotron cooling. So that's nice that everything seems to fit together consistently. Also, our model suggests a typical 10 to the 51 erg explosion energy, a rather high, approximately 21 solar mass ejecta mass, and it's consistent with the pulsar breaking index of around in approximately 1.9. So this large ejecta mass suggests that the progenitor was probably isolated, otherwise it would have probably donated the mass to its companion. And also that it was probably a red supergiant that had perhaps not quite massive enough to lose lose the mass in the wind. And finally, I don't think I have too much time left, but I just will say a little about the timing analysis that we did with our NuSTAR data. So here you can see a plot showing the clear detection of the pulsar spin period in both NuSTAR observations. And we also show the pulsar pulse profiles and a couple energy bands. So what I found interesting here is that the pulsar period derivative derived from the NuSTAR data alone is actually larger than the period derivative derived very precisely from radio data alone in 2002. And the reason that's interesting is that if this period derivative really is increasing and not just due to some perhaps glitching activity, then it implies that the breaking index is less than 2 and therefore significantly different than the canonical n equals 3 pulsar breaking index that you would just get from magnetic dipole radiation. So this is interesting to mention because it's actually consistent with the value of 1.9 that we derived from our SED modeling alone. And this is, of course, these breaking indices are notoriously difficult to measure. So any hints at this are interesting. And I just want to emphasize that we're not claiming to have definitively constrained this breaking index from either the SED modeling alone or just from these 2 timing observations alone. These are, as I said, very difficult to measure. But it's interesting that the X-ray timing data and the SED modeling are pointing in this direction. And we're actually currently working with some radio timing data to measure this much more precisely and definitively. So finally, here is the pulsar indicated on the famous pulsar PEP dot diagram. You can see it indicated here, pulsar J1930, and you can see the whole diversity of the neutron star zoo throughout this diagram with the lines of, for example, a constant magnetic field or a constant pulsar age indicated. So of course, the canonical value in n equals 3 corresponds to pulsars just moving to longer spin periods along these lines of constant magnetic field. But if, in this case, say if n equals 2, then it's moving horizontally and could be, an indication of, for example, possibly an increasing magnetic field or some other interesting physical phenomena could be indicated by this value. So it'll be very interesting if we can confirm this result and figure out where the pulsar is evolving in the diagram. And only a handful of other pulsars, I think only maybe 5 or 6 have well-determined breaking indices, and it'll be interesting to compare it to its cousin, the Crab, which has an index measured around 2.5, so moving in a slightly different direction, a little bit closer to the canonical value. So I'll just quickly conclude with a reminder of some of our results. We found that G54 is currently accelerating leptons up to at least 400 TeV. And the SED modeling suggests some interesting parameters for the system, such as the initial spin period, the large ejecta mass, and possibly a braking index less than 2. So we'll continue studying the system with further SED modeling to better explore the parameter space, and currently also working on a radio timing analysis to precisely measure the pulsar braking index. Thank you.
Thank you so much, Jason. Lots of virtual claps. I'll open up the floor for questions. We already do have one question in the chat. Reynolds, I assume Chris Reynolds, do you want to unmute and ask your question?
Yeah, I'm Steve, not Chris, but that's all right. Just wondered how the output pulsar wind nebula size compared to the observed size of the object, which is, of course, not very round, but that's another issue.
Yeah, so we do assume this is a one-zone model. We do assume that it's basically perfectly spherical. We got a very good fit to the size of the Pulsar Wind Nebula. I think it's about 1 arc minute. No, I think I mean actually, I better not say the exact, but we got a very good fit to the size of the Pulsar Wind Nebula, but don't quote me on what the size is right now. But yeah, we were able to get a very good fit to the size.
Good, thanks.
Okay, Steve has his hand up. To Kirby.
Yes, hi. Great talk. I have a quick question about your multi-wavelength synchrotron and inverse Compton fitting. In that fitting, did you allow the ambient infrared photon field density and temperature to vary freely? Did you put any constraints on those? And how do those values compare astrophysically to local values at the solar neighborhood?
So yes, those are free parameters, and we found you can see this external photon field temperature of around 2700 Kelvin. And what we think is happening here is that, as I mentioned, this system is embedded in a dusty environment with some OB stars. And what we think is happening is that, of course, the OB stars are much hotter than the temperature of this photon field. But what we think is happening is that the photons from the OB stars nearby are being reprocessed in this very dusty environment, and you get effectively a lower temperature external photon field.
Great, thank you.
Okay, and we have time for one last question by Rick Rothschild. Go ahead.
Can you tell, in your spectral modeling, can you tell the difference between a break at 5 keV and just an exponential rollover?
Yes, but it's not an exponential rollover because the pulsar wind nebula is detected way above 5 keV. We detect the system up to around 70 keV. So it's definitely a two-component power law with a break there.
Okay, and one other thing, you have on the screen the period of 70 milliseconds, but your new star was 139 or whatever. Is that just overtones and you couldn't get down to 70 milliseconds?
No, this is P0. This is the initial, what we derive an initial spin period of the system. The period today is 137 milliseconds, but from our modeling is a time-dependent model. So what we do is we take the observed period and period derivative today, and then work backwards with a braking index and spin down time scale, and that lets us derive this initial spin period of 70 milliseconds.
Gotcha. Thank you.
Okay, thank you so much, Jason. That was a great talk and really interesting engagement with the audience. Appreciate that. We are going to go on to our next speaker. This is Priya Ghosh. So Dr. Ghosh has a bachelor's of science in chemical engineering, and she got her PhD in nuclear engineering from Kansas State University. She's developed several types of neutron detectors and is currently a postdoc at UMBC and NASA Goddard Space Flight Center, focusing on nuclear cross-section experiments for the study of cosmic rays. And she'll tell us more about that today. Go ahead, Priya.
Thank you for the introduction, Carolyn. Can you see my screen?
Yep, looks good. Go ahead.
Okay, so I'm going to first talk briefly about the astrophysics mission Tiger ISS. which is a cosmic ray detector that will determine elemental abundances up to very heavy elements. And then I will talk about the program that we have started at NASA Goddard to perform cross-section experiments that are important not only for astrophysics, but also for planetary science missions. So in the last century, there have been monumental advances in the understanding of our galaxy and its many physical phenomena. And these revelations have been made possible partly due to galactic cosmic rays, or GCRs. Since they were first discovered by Victor Hess in 1912, when he was flying a balloon and his detector recorded counts that increased with increasing altitudes, since then, many cosmic ray detectors have been built with increasingly advanced technological capabilities that have helped us further our knowledge of the chemical makeup of our galaxy. The figure on the left is shows the chemical composition of the solar system in dashed lines, determined by studying lines from meteorites and the solar photosphere, and the chemical composition of the Milky Way galaxy shown in solid lines, determined by measuring cosmic rays using particle detectors. Now, both the solar system and GCR abundances show the even-odd effect, which arises in the solar system from stable end products of stellar nucleosynthesis. And the fact that the GCR abundances reflect a similar trend indicates a stellar origin for the GCRs as well. However, the differences in their abundances, especially in the overabundance of elements in the lithium, beryllium, boron group and the scandium, titanium, and vanadium group, which are uncommon stellar nucleosynthesis products, indicates the importance of propagation in the interstellar medium. So using the current observational data and nuclear data that is used to interpret the observed data, we have been able to paint a picture of the origins of the elements and what the galaxy looks like, which at the moment is a bit blurry, but not because our detectors aren't good enough. In fact, there is some exciting new progress in cosmic ray detection capabilities. Currently, excellent elemental abundance data up to Z equals 30 exists from various instruments such as ACE-CRIS, CALET, and AMS-2. And for Z in between 30 and 60, results from TIGER and Super TIGER must be combined with measured data from missions such as ACE-CRIS and normalized. And for Z greater than 60, the TREC detector on Mir has measured data with single element resolution at the highest charges. So now the Trans-Iron Galactic Element Recorder for the International Space Station, or TIGER ISS, which was recently selected as a Pioneers mission, will launch to the ISS in 2026, and it will address the scarcity of ultra-high galactic cosmic ray data in several ways. Firstly, by combining silicon strip detectors and Cherenkov detectors, TIGER ISS will be able to measure charge with uncertainty on the order of 0.2 charge units from boron all the way up to lead. And then the wide range of measurements from a single instrument will enable normalization that will resolve discrepancy between previous instruments like that of ACE-CRIS and Super TIGER CALET. And lastly, TIGER ISS will have lesser systematic uncertainties in its results, primarily due to the lack of atmospheric overburden on the International Space Station. So TIGER ISS will be the first instrument to provide elemental resolution data from boron to lead in one single detector. And so the data we will observe will be the most accurate observation to date. So now the observational data needs to be converted into a meaningful understanding of the galactic processes. For example, the spectrum of each isotope contains information about the contribution of various parent isotopes in terms of fragmentation, decay, and other processes which result in a very complex history of each observed element. One of the most violent reactions that happens in the interstellar medium is proton spallation of the primary cosmic rays, producing daughter isotopes or secondary cosmic rays, which are then detected by our detectors on Earth. Now, in order to deconstruct this history and origin, we need to know the probability of interactions with protons in that interstellar medium, which is called cross sections. Now, sadly, even though there is excellent observational data, the limiting factor in deconstructing this history is actually the lack of availability of cross sections. And the current state of nuclear data as obtained from X4 shows a lot of regions that have no data on certain reaction channels or less data at higher energies. For example, in this reaction of natural iron proton spalling to 51 chromium, a lot of experimental data don't agree with each other, or they have high uncertainties, and the models don't agree with each other. So in total, it creates very unreliable data. And for interpreting cosmic ray data, one of the most comprehensive toolkits is GalProp, which is a cosmic ray propagation code containing various models, and it incorporates physical phenomena like reacceleration and diffusion in the galaxy. The most recent online available version contains proton spallation cross-sections to about z equals 30, experimental ones, experimental data, I mean. And GalProp also uses nuclear codes and formulas like the Nuplex code and Weber and Silverberg and Sau codes to have a continuous cross-section values across all energies and species. But again, with many reaction channels lacking experimental data, the accuracy of extracted data remains uncertain. So here at NASA Goddard, we have organized a group of experts from Berkeley Lab, Johns Hopkins Applied Physics Lab, and Stanford to perform cross-section experiments that address these shortcomings. So here's a list of the highest priority measurements right now. For Tiger ISS, which will launch in 2026, in the first year, the production cross-section of isotopes below z equals 58 will be more important because of the limited statistics. But at the end of 3 years, the most abundant isotopes of the S and R process elements will be important in the energy range dictated by Tiger ISS detection technology, which is 200 MeV to 10 GeV per nucleon. The second range of interest is the ratio of electron capture isotopes and their decay products. In particular, the 51 vanadium to 51 chromium and 49 titanium to 49 vanadium ratio is used to assess the importance of energy changing processes, like reacceleration in the interstellar medium and adiabatic energy losses in the heliosphere. There have been some inconsistencies in the calculation of reacceleration rates between the vanadium to chromium and titanium to vanadium ratios. And these have been hypothesized to be due to large uncertainties in their current predictive cross-sections. In fact, there is one paper that has calculated that reducing the 49 titanium fragmentation cross-section uncertainty by 15% would resolve this discrepancy. And this is a dilemma that has been presented since 2003, but hasn't been addressed yet. So the other area of interest is the electron capture isotopes in the sub-iron region. This is also a region that happens to be of interest to the planetary spectroscopy community, especially right now for determining the composition of the asteroid Psyche, which is NASA's first mission to a metal-rich world. So to address these shortcomings, at NASA Goddard, we are undertaking an effort to conduct proton spallation cross-section measurements that are of interest to both astrophysics and planetary and other missions that require such cross-sections. So the first of these measurements we performed this summer at Brookhaven National Lab. Our focus here was 3 monoisotopic targets: cobalt, aluminum, manganese, and a mixed isotopic target, chromium. Cobalt, for example, has a lot of available data at lower energies, as shown in the figure on the left, but not at higher energies that matter astrophysically. Which is where we performed our measurements shown in dashed lines. And in this experiment, what we did is we had a proton beam from 250 to 2000 MeV bombarded on metal targets. And this is what astrophysicists define as being indirect kinematics. And the fragments that result from proton spallation, if radioactive, we measured them using gamma ray detectors. We undertook several measures to ensure the least possible errors. One of them, for example, is the use of thin targets with high purity, so that the contribution of secondary products to nuclide production is minimal and thick target corrections are not required. One of the sources of errors we did have for our particular measurement is that we did not have a high purity germanium detector present on site at the NSRL facility. And so we had to use cerium bromide detectors, which has energy resolution of about 4% at 662 keV, compared to HPG, which has 0.15% energy resolution. So the top figure shows the cerium bromide measurements for the shorter-lived isotopes that we had to measure on site, and several of the peaks contained more than 3 or 4 daughter products. So that would increase the uncertainty. We hope that the next time we do this measurement there, we will have access to a HPG, and that will lead to even lesser uncertainties. The next experiment we performed was the Na61 experiment at CERN as part of Michael Unger's group, and it concluded just last week. The main beam was lead. It was produced by the SPS beamline shown here in orange, and it is then bombarded on a beryllium target, which produces the secondary isotopic beams that for our purposes act as the primary cosmic rays. And we wanted to produce these astrophysically important beams shown in the list on the right. This is an example of direct kinematics. And after the secondary isotopic beams are produced, they are routed through the H2 beamline, where we have rigidity selection. And then time-of-flight scintillators are used to resolve the isotopic beams before they are incident on the hydrogen target, which in our case was polyethylene. And then the resulting fragments will then be studied using magnetic rigidity spectrometers, and we will be able to determine cross-sections for each reaction channel. So I wanted to show this figure that we obtained from last week. We have been able to separate secondary beam isotopes up to silicon within acceptable error margins, which is a vast improvement from the 2018 run. And this has been due to an upgrade in output electronics and their timing. So we do expect to obtain very good proton spallation cross-sections for Z up to silicon from this run, for a lot of which data does not currently exist. And the last experiment that we have planned for next year is the 52 chromium bombardment of a liquid hydrogen target at the facility for rare isotope beams. 52 chromium, as I had mentioned a few slides earlier, is important for constraining the reacceleration models, and is a major contributor for titanium-49. Chromium-52 targets are quite expensive to buy, especially for multiple energies. So the most cost-effective way to measure proton spallation of 52 chromium is to use a beam instead of using targets. And FRIB is one of the institutions where such a beam can be generated. So I also wanted to mention that we very carefully select which reaction channels to measure at which facility, because the type of data we need can be more or less cost-effective and low uncertainty, depending upon which kinematics, which energy, and hence which facility we measure them at. So finally, we are looking to collaborate with institutions that have such capabilities. And if anyone has any ideas for any reaction channels that are important, or any facility that might be able to help us take these measurements, please do contact me. And that's all I have.
Thank you, Priya. Lots of claps online. Any questions for Priya? I don't see any in the chat yet. While we wait, I did have a question. So while you're doing these measurements at the beam facility, what are the timescales for these isotopes that you're looking at? It seemed like you needed a germanium detector on hand. So is this seconds, minutes, hours, days? Like, what decay times are you
So for
trying to
this
probe?
particular measurement at Brookhaven, what we do is take immediately right after irradiating the targets, we take a set of like 1 minute, 1 minute, then 2 minute, 2 minute, 5 minute, 5 minute, 10 minute, 10 minute measurements so that we can look at the decay of these products. And so for the shorter lived isotopes, which can range from minutes to just about an hour, we want to measure them on site, and the facility does not yet have a HPG. And so what we do with those is we just carried our own cerium bromide, and then the rest of them, which are longer lived, we have brought them back to NASA Goddard, and we have an HPG with us there. So we're using them right now to measure the longer lived ones.
Any one question from the audience? Okay, one more question, Priya, then. Once you get the results of these cross-section measurements, you mentioned like Galprop, et cetera. How do you get this to the community? How do other people use these measurements? Are they going to be included in these codes in the future?
So we'll obviously publish some papers when we get our results. But yes, as soon as we have data, we will incorporate them into Galprop. In fact, the next version, which I think is V58, is coming out in the summer of next year. And so if we'll have data from the NSRO, the Brookhaven experiment by then. So we'll probably include those data in there.
Okay, thank you so much, Priya. Thanks again. And we'll move on for our final speaker today. This is Myra Jones. Myra Jones is an undergraduate student at Vassar College. She's studying physics, astronomy, and French. And from Myra's first research as a high school student until now, she's already amassed an impressive portfolio working with the South Pole Telescope and the SETI Institute. And she's recently focused on understanding the influence of metallicity variances on the simulated circumgalactic medium. So she's on track to earn her bachelor's degree in the fall of 2025. And she's going to tell us today about a research project that she's been involved in that's a bit different than our usual topics. But Mariah, can you please unmute and share your screen?
Of course, yes. Hello.
Great.
Okay, so okay. I'm assuming you guys can see my screen here.
Yeah, just once you go into presenter mode, that looks great. Okay, take it away.
Beautiful. Okay, perfect. Yeah. Yes. So I was working on a project on the circumgalactic medium. However, that project, there's some delays in the results and such, and that professor's on sabbatical. So I'll actually be talking about my summer project, which I did at the SETI Institute, which involved investigating the stability of Trojan and Horseshoe co-orbitals in extrasolar multi-planet systems. Okay, so firstly, what is a co-orbital configuration? Well, they involve two or more bodies that share the same orbit around a host. Now, these hosts can be planets or stars, and these bodies can be planets or moons or anything of that sort. And these bodies that are sharing the orbit are known as co-orbitals. Now, I'll be focusing on two specific kinds of co-orbitals. The first is known as a Trojan or tadpole, and they essentially oscillate about the stable Lagrangian points L4 and L5 with an angular separation of 60 degrees. And the second type of co-orbital I'll be talking about is they are horseshoe co-orbitals, and they have more complex paths. They oscillate 180 degrees apart in longitude, and they essentially exchange their orbital energies during close encounters, which causes the horseshoe shape. Now, there are co-orbitals found within our solar system. 5 planets are known to host co-orbitals, asteroids. And of these 5, however, only 3 are able to host stable co-orbitals. And what is the reasoning for this instability? Well, it's because Saturn and Uranus, they're in near resonances with Jupiter and Neptune respectively. And Saturn specifically lacks stable Trojans because of its near 5:2 period ratio with Jupiter. And this essentially results in strong gravitational perturbations that destabilize the co-orbitals. Now, this leads me into my research question, which was basically to figure out whether or not a system's resonance has any influence on long-term co-orbital stability, specifically in extrasolar planetary systems. Now, in order to answer this question, we modeled 5 multi-planet systems of varying resonances. So TRAPPIST-1, which is in 2-body resonances, they have 7 planets. Kepler-11, which is a 6-planet system, not in resonances. Sorry, this is in the way, but I believe this is 80. Yeah, okay, Kepler-80, which is in 3-body resonances, which are weaker than 2-body resonances because their associated potential experienced by any of the 3 bodies is proportional to the masses of each. So because there are 3 bodies, there are more distribution. Kepler-90, Kepler-80 has 5 planets. Kepler-90, which is also not in resonance, and they have the same number of confirmed planets as our solar system. And they're all scrunched into a distance equal to that of the Earth's semi-major axis. So many planets kind of squished into 1 AU, so very crowded system. And then HD 110067, which is in 2-body resonances, and they have 6 planets. So now for my process, I first acquired the initial conditions for these systems from NASA's Exoplanet Archive, and then I simulated the systems by adding 20 hypothetical co-orbitals for each planet using rebound. So for each of the many planets, I added 20 hypothetical co-orbitals, and I distributed them out to one Hill radius, which is essentially just the mass of the co-orbital body divided by 3 times the mass of the star raised to the 1/3 power. So the initial co-orbital semi-major axis is equal to that of the planets, and the co-orbital that is farthermost out is increased by 1 Hill radius. And then I plotted the eccentricity, inclination, and difference in mean longitude of the co-orbitals within the systems. And the difference in mean longitude is the mean longitude is just the average angular position along the orbit. And then I wanted to assess the stability of the systems using lifetime plots. I wanted to visually identify where these systems, or where each particle in the system became unstable. So here are my difference in mean longitude plots for TRAPPIST-1b over 10 to the 6 years. Again, TRAPPIST is in 2-body resonances. And now these patterns on these graphs here, well, firstly, I have on the x-axis the time, and then on the y-axis, I have the mean longitude of the co-orbital minus that of the planet. And now the patterns here represent different behaviors of the particles. So here we've got a stable Trojan that remains stable throughout the entire duration of the simulation. Here we have a horseshoe that was initially stable, but it ends up dying out around whatever time this is right here and time this is right here, assuming you guys can see my mouse. And then down here we have no stable co-orbitals. There are no patterns identifiable, which means that basically from the onset of the simulation, the particle was shot out into outer space or collapsed or something happened to it and it's no longer present and no longer orbiting this body. Now for Kepler-90f, over 10 to the 5 years, the system is not in resonances, and we can see a lot of different patterns here on these plots. So here we have a particle that is alternating between a Trojan and a horseshoe. So these single lines here represent the Trojan, but the double lines are the horseshoe here, and we see how it's alternating, especially down here. This is a Trojan, and then here is a horseshoe. Very interesting. Then we have a particle that switches from a horseshoe to a Trojan. So surprisingly, it starts off as a horseshoe, and then it gradually, as time goes on, switches off to a Trojan. Here we have stable Trojans throughout the entire duration of the simulation, and up here we have many, many stable Trojans. And one other thing I want to point out is we can see here that as the particles that are closer to the host are generally Trojans. So they start out as Trojans, and then as you increase your distance from the host, they sort of switch off to becoming a horseshoe, or they alter their configuration from Trojan to horseshoe generally. And we can also see that as you are closer into the host, you are generally more stable. And as you increase your distance out, as you increase your semi-major axis, you increase your, I guess you increase your chances of being unstable, based on these plots here. And so we can also infer that that Trojans are generally more stable than horseshoes because they're more closer into their hosts. And now for further assessing the stability using lifetime plots, I first had to find the stability threshold, which is just the smallest difference in mean longitude able for the co-orbital configuration to remain stable. And actually, in a previous paper by my mentor, he defined 5 as the mutual Hill radius limit for stability. So to find this threshold, I just multiplied 5 by the Hill radius scaled by 5 times the Hill radius, which is scaled in the semi-major axis regime, if that makes sense. So just the Hill radius divided by the semi-major axis times 5. And then I also made lifetime plots, which had the semi-major axis on the x-axis and the lifetime on the y-axis. And I found this lifetime by taking the stability time, which the stability time is just the earliest time that the difference in mean longitude is at that Hill radius limit for stability, and dividing that by the host of the period. And then to visualize the instability, I added horizontal lines that serve as stability indicators. And I found these lines by taking the total simulation time and dividing that by the period of the host. Now, here is a lifetime plot for TRAPPIST-1, which is in 2-body resonances. Now, how to read this graph is for each point on the graph, it corresponds to a colored dotted line. And so each color represents a planet of the system. And so this blue here is for 1B, and the orange is 1C, and so on and so forth. And so the lines the dots that are along their dotted line represent stable particles, but the ones that fall below their line, the ones that fall below the stability threshold, represent particles that are no longer stable. So for 1B, we see a bit of stability, but generally it's not a really stable system. Most of the dots are falling below their respective indicated lines. For Kepler 80, which is in 3-body resonances, we have a bit more stability. The innermost planet, Kepler 80f, is able to remain stable for almost, all of the particles are able to remain stable for almost the entire duration of the simulation. However, as you go farther out, that is not really the case with the planets farther out. Now with Kepler 90, which is not in resonances, we see a drastic change. Essentially, the planets are able to maintain stability for their co-orbitals for pretty much the entire duration of the simulation. Obviously, there are outliers, this orange color here and the gray color and some of the pink and purple, but generally, we see, in comparison to the other 2 systems and their varying resonances, the particles are able to remain stable, or have a much easier time remaining stable. This leads me to my conclusion. I was able to determine that orbital resonances have a significant impact on co-orbital stability. And co-orbitals are generally less stable in resonant systems, with Trojans generally being more stable than horseshoes. Again, this is having to do with the Trojans being closer into their hosts and horseshoes being farther out. And generally, as you're closer into your host, you are generally more stable. So this is something that potentially could be looked more into, seeing how the effect of the semi-major axis has on the stability, potential avenues to look more into. But why do these resonances have such an impact on the stability? Well, it's because the period ratios lead to perturbations within these systems. So co-orbitals of one planet are also in or near resonance with other planets, which potentially cause dynamical chaos. And essentially the environment is too hostile for the co-orbitals to remain stable, or for the co-orbitals to remain in their orbits with their hosts. And this stability can be linked to dynamical interactions and resonances within these extrasolar multi-planet systems. And for some future work, the importance of this, with the linkage to the dynamical interactions in the systems, enhancing or expanding our knowledge of these co-orbitals could actually inform future observational strategies for their detection in extrasolar planetary systems. And for future work, we could, if this project were to expand or continue, some avenues would be to further explore the relationship between the semi-major axis of the host body with respect to the stars and the co-orbital bodies with respect to their hosts, and also to adjust the code for account for more eccentric orbits rather than just assuming circular, which is what this project entailed. And that is all. I'd like to thank the SETI Institute, my college, Vassar College, the National Science Foundation, DPS, their travel grants, and Zaria, my cat, who actually lives on campus with me. She's here in my room now. This QR code is to my website if you want to check that out. I have my CV, my LinkedIn, all that stuff. And then this website here is my repo for the entire project. So I have all my codes, all my results, all my plots and whatnot. Yeah, and I'll take any questions now.
Thank you so much, Mirai. Any questions from the audience? I know that this topic is a little out of our own expertise, but thank you for making it easy to understand.
Oh, of course, of course.
Okay, while we wait for someone else, I did have a question. You kind of mentioned at the end about the observational potential here. Are there observations that we can make to kind of validate your simulations or look at these particles? Is there anything that we can see for these particles?
Yeah. So I actually love this question because everyone always asks this question. And I actually intend to, I love the intersectionality between observational and theoretical astrophysics. With that being said, I don't know much about the observational piece. I know that essentially I know that being able to understand how these co-orbitals interact in the systems, and if these co-orbitals are likely to exist in certain systems. I know that knowing that for a particular system, knowing where the co-orbitals are more likely to exist or remain stable, we can infer that, or we can know which systems to look at. Does this make sense? So knowing where the co-orbitals are likely to or should exist and remain stable, we can take that system and know that they should be there, so we can look for them there, as opposed to systems that we know are in resonances or kind of have gravitational instabilities or dynamical gravitational chaos, that the co-orbitals might not exist there. So we can infer not to look for them in those systems, if that is making sense. So there isn't, my project doesn't really look into the observational aspect of it or future work for these observational strategies, but I know that there is a link there for a scientist in the future to look more into, if that answers your question.
Yeah, okay, thank you so much. Anyone else have a question online? All right, well, we can end a minute early today. Thank you for the 3 speakers. Really, really appreciate you guys taking the time to put together the slides and present on your work. And thank you for everyone who was able to make it today to support your early career scientists in the community. Everyone have a good day. Have a good holiday season. We'll talk soon.